Okay, so for chapter 12, section 4, what we want to introduce is a, a reference frame of motion. We want to introduce three important vectors that are going to be that are present throughout the path of a projectile. So if you take a look at my diagram here, what I have is just imagine some projectile that starts at point P, and what we're seeing is the path of this projectile. Okay? So as I mentioned, so throughout the entirety of that path, there are three vectors that are always present. And what we're gonna do for this part A of this video is we're gonna go ahead and just list some properties of each of these vectors. Then we'll probably do some examples with the first vector. And then in part B, we'll come back and we'll do some more examples. Ready? Let me just again make sure you understand. We are going to try to build a reference frame, a geometry basically that is going to be present throughout the entirety of some projectile in motion. Now, we refer to this, or at least the way I was taught it, was as what we call a TNB frame. Now, in physics, if I recall correctly, it's normally referred to as a Frenet frame. I believe that I'm pronouncing that correctly, Frenet, after the physicist Jean Frenet. So let's jump in. Ready? So the first vector that is important to us is what we call the unit tangent vector. And what I want to go ahead and do is tell you how we're going to denote this vector. So we use a capital T, so T of t. Let's define it, and then I will give you some properties of it. So how is the unit tangent vector defined? Again, think back to you start with a vector valued function, r of t. To define this unit tangent vector, it's simple enough. It's just going to be r prime of t divided by the magnitude of r prime of t. Now, what we want to do now is list some properties of this vector. Well, one of the properties is, of course, you can see it from the title. It's unit tangent vector, meaning it's a unit vector or of length 1. But the second property, which is more important to us, is, let's go ahead and look at the picture really quickly. So again, imagine this this projectile starting at point P, and notice how T of t, notice how it points in the direction of motion, right? It's basically, it's letting us know which direction we're going to proceed from where we are. Now, you have to be able to envision that as your projectile moves, your vector, T of t, moves with it, right? So by the time your projectile has reached this new point where I'm highlighting, you can imagine that your unit tangent vector would now be pointing in this direction, again, giving you insight as to the direction of motion. So points in the direction of motion. Make sense? Now, let's go ahead and talk about the second vector. So let's give it a name. The second vector that is extremely important is what we call the principal unit normal. Let me fix that, normal vector. Okay, now let's go ahead and let me go ahead and list how we're going to denote it, and I will probably carry this the properties onto the next page where I have more room. So we denote the principal unit normal vector n of t. And now let's go ahead and define it. So n of t is going to be, if you already have the unit tangent vector, then it's t prime of t over the magnitude of t prime of t, which should make sense that that's just the second derivative of r, right? R double prime of t over its magnitude. Okay, so I'm going to go ahead and list the properties of this vector on the next page. So let's go ahead and do that now. So if again, we're back to point P. So if your unit tangent vector is going to point in the direction of motion, what does this principal unit normal vector, what is that doing for us? Well, if we're in a plane, it's going to point in the direction of concavity. So let me go ahead and write that. So some of the properties of this n of t, well, okay, I'll go ahead and list it. Of course, it is still a unit vector, so length 1. And then the more important property for us is it always points in the direction of concavity. So you can kind of see the concavity of your curve here. And maybe what I will do is, to make sure you understand what I mean in terms of pointing in the direction of concavity. So here is, I'll just draw something concave down, and I'll draw concave up. And then you would expect, if it's pointing in the direction of concavity, that n of t would be pointing like this. Now this is nice. This is important. However, the way you would think about this property in space is different than the way obviously that we would think about it in 2 dimensions. So in 2 dimensions, n of t is again pointing in the direction of concavity, but in space, it's pointing in the direction of turning. So let me write that. So, or in space, the direction of turning. Now, one of the other properties is that it helps us find curvature. Which we will come back to in a later section. So, all right. The final vector, which is, we won't spend a lot of time discussing, is going to be the binormal vector, or b of t. I'll go ahead and define it. So the binormal vector is just going to be the cross product of the previous vectors. And of course, properties, because it's a cross product, what you can expect is that your binormal vector is going to be, normal to the other two vectors, right? It's going to be, perpendicular to t. And end of t. All right. So again, this is the TMB frame. My apologies. I know definitions are not always exciting. Let me say just a couple quick things really quick before we start trying some examples. You will notice that back to just looking at t of t and n of t. You will notice that they are orthogonal to each other. But this is actually only the case when you're dealing with a projectile, right? If this projectile has a constant speed throughout its path, then you'll notice that these, in the reference frame, these two vectors are going to be orthogonal to each other. If you're dealing with variable speeds, right, if this projectile is speeding up and slowing down, that won't be the case. Let's go ahead and practice. Let's practice using or finding the unit tangent vector. Ready? So again, we have everything defined here. We're going to jump in to the first example. So the first example says, find the unit tangent vector to the curve given by the following vector valued function. All right. Well, you can see that we're going to need, we're given r, we're going to need r prime, and we're going to need the magnitude of r prime. And so let's go ahead and get those first, and then we'll build t. So let's start with r prime. So moving quickly, so the derivative of t with respect to t is just 1. So that's going to be 1i, or just I, plus the derivative of t squared is going to be 2t j. All right, so there's r prime. And now let's go ahead and find the magnitude of r prime. So magnitude of r prime. Well, it's simple enough. We're, as you know, you're just taking if you want to find the magnitude of a vector, it's just going to be the square root of the components squared, right? So let's start with the I component. So that's 1. So that's going to be 1 squared plus now let's go to the j component. That's going to be 2t squared. So what is it? It is the square root of 1 plus 4t squared. And now we got it. Now we can just build our unit tangent vector. So it's going to be r prime over its magnitude. And again, my thoughts would be to, let me write it up here. My thoughts would be to write it like this. 1 over magnitude of r prime of t times r prime of t. You'll find that even if when you're looking up your answers in the back of the textbook, they're normally going to be written the way that I have it here. So, all right, let's go ahead and do that. So that's going to be 1 over the magnitude, so 1 over the square root of 1 plus 4t squared, multiplied by r prime, so multiplied by I plus 2t. And there you go. So this is t of t. Okay, so they go a little bit farther. Now, of course, your unit tangent vector, this is, notice that parameter, notice that t variable there. So all we want to do for the second part of this question is just evaluate it at when t is equal to 1. Ready? So all I'm going to be doing is I'm just going to go ahead and produce this. So t of 1 is going to equal, well, if you plug in 1 into that square root, so that's going to be 1 squared times 4 plus 1, so that's just the square root of 5. So 1 over the square root of 5 multiplied by I. 2 times 1 is 2, so plus 2j. Okay. So not too bad. I don't think you will find that too bad. It would be a shame. It would be a shame to just get into the recipes and not look at the geometry, right? So here, notice that you have this your path, right? Your curve, and then here is. So this is the path of r of t. And then now look at t of 1, and you can there, just like I was mentioning prior, you see how you can see the direction of motion pointing, so that is pointing the direction of motion. All right, so one more and then we'll take a break. So example 2, let's see what they are asking of us. Well, they want us to find, so we want to find a unit tangent vector, and then, well, I'll tell you what, let's come back to the and then part. So let's find t of t. All right, so we have r. Let me go ahead and list r prime. And let me go ahead and list the magnitude of r prime. All right, let me go quickly through this. So r prime, so taking the derivative of r, so that should be what, negative 2 sine of t, I direction. We got plus, so it's going to be 2 cosine in the j direction, and of course the derivative of t is just 1, so plus k. All right, and the magnitude of r, it's going to be negative 2 sine t squared plus 2 cosine t squared plus 1 squared. Okay, if you were to miss this part here, then in this magnitude portion, then you would create a lot of additional work for yourself. So what you should notice is that we're going to end up squaring a sine, squaring a cosine, which you should start to train yourself that probably means that we're going to be using a Pythagorean identity. So I'll go ahead and, since I mentioned I mentioned it, I'll go ahead and write it. So this becomes, after you square, this becomes 4 sine squared plus 4 cosine squared. I've ran out of room, so I'm going to come down here. Actually, I'm going to erase it and start over. So that's going to be equal to 4 sine squared plus 4 cosine squared plus 1. Okay, so what's going to happen here is I'm just going to factor out a 4. So what does that look like? So now I have 4 sine squared plus cosine squared plus 1. All right, so this is about to become the square root of 5. I hope it makes sense to you that sine squared plus cosine squared is just 1. And so that means 4 times 1 plus 1. So what does it equal? It equals the square root of 4 plus 1, or just 5. Okay. So let me go ahead and build my T of t, and then I'll get back to the question and figure out what is it that they want us to do. So that's 1 square root over the square root of 5, and now multiplied by r prime. So that's going to be negative 2 sine of t plus 2 cosine of t plus k. All right, so let's get back to the question. So find the unit tangent vector, done. And then find a set of parametric equations for the tangent line to the curve, which is a helix in this case, given by the following vector valued function at the point square root of 2 pi over 4. Interesting. So how do we hopefully, because we can become saturated with material, but what do they mean find a set of parametric equations? Well, it should make sense that a set of parametric equations for a tangent line. So if you don't mind, let's take a look at the geometry of what this question's asking. Let's see if it can. So you can see the blue tangent line, and you can see the point that we're given, and what we want is the equation of that tangent line. We want the parametric equations. So what should you be, what should we be thinking? We should be thinking x equals y equals z equals. All right, so let's go ahead and I'm gonna grab my T of t, and we're gonna go to the next page so I have a little bit more space. So let's think about it really quickly. The parametric equations, we worked with this back in chapter 11. What do you need if you want to find the equation of a line in space? Well, you're going to need a point on that line. Well, that's okay. We're given that. That was given to us in the problem. But we also recall we need that vector that runs parallel to that line. Now, we'll find, so to make sure you understand, this point is given. This vector will be derived from the unit tangent vector. How would you derive the unit tangent vector? So let me go ahead and write it. So at the point, the square root of 2 pi over 4. Are you ready? So I need to substitute something in for t. In fact, I'm going to give you a second to consider this question. Ready? What should I plug in for t into this vector? Go back, take a look. What should you be plugging in? Interesting. So maybe we can phrase the question differently. So at this point, this is a very important question. I do hope I have your attention. So at this point, what does t equal? Well, you can see that just look at your z. So we have the square root of 2. This is our part of our I component, part of our j. But notice that we could, when setting this equal, we could set t equal to pi over 4. We can set our k components equal. We know exactly what t is. We know what to plug in here. So what is it equal? It's equal to pi over 4. How did I do that again? How did I do that? I'm just noticing that t is equal to pi over 4. All right. So where does that leave us? Well, for our job now is going to be to take t at pi over 4, and we're going to be plugging it in for t. Ready? Let's go ahead and do that. So this is, what is it that we're actually doing? We're going to evaluate t of pi over 4. All right. So if you plug in pi over 4, you end up with, you still got 1 over the square root of 5. And now the sign of pi over 4 is the square root of 2 over 2. So that negative 2 positive and 2, so we're canceling the 2's, leaving us with just negative square root of 2i. Plus cosine of pi over 4 is again the square root of 2 over 2. So 2 times the square root of 2 over 2 is just going to be equal to the square root of 2. And of course, there is nowhere to plug pi over 4 in for the k component, so it's just plus k. All right. Now, let's get back to our parametric equations. We're almost there. Notice something. Notice that I used s here. I believe in chapter 11, the parameter that was chosen was t. The only reason we're not using t is because I don't want to confuse t here versus t here. I don't want there to be confusion about that. So here we go. We know the point, and this is the vector that is running. Remember, if it's running normal, that's right, it's pointing in the direction of motion, so it's going to be parallel to the line. So ready? Let's go ahead and list. So x sub 1 is equal to the square root of 2. Y sub 1 is equal to, my apologies, let me actually change the color too. So let me say that again. So x sub 1 is going to be equal to the square root of 2. Y sub 1 is going to equal the square root of 2. And z sub 1 is going to equal pi over 4. And now, in terms of our vector a, A is going to be equal to, well, do you recall? So that's going to be this I component, so negative square root of 2. B is going to be equal to this j component, so that's just the square root of 2. And finally, C is going to be equal to this k component, which is just 1. Ready? We have everything we need to plug into our parametric set. So the answer is x equals the square root of 2 minus the square root of 2. Again, I'm using s instead of t. Y is equal to the square root of 2 plus the square root of 2 s. And finally, z is equal to pi over 4 plus s. There we go. There is your, I hope it makes sense that this is a line. This is now this is the equation of a line in space using a parametric form. Okay. We are going to take a break, and I'll see you in the next part of this video.